Massive stones were moved with a precision that defies simple explanation. This video uncovers the unearthed blueprints behind how ancient engineers designed machines of stone, revealing the brilliant methods used to build our world's most enduring monuments. You will learn the exact principles that allowed civilizations to lift and place blocks weighing hundreds of tons, secrets that reshape our entire view of the past. How did they calculate the perfect lever point to lift an obelisk? What hidden knowledge allowed them to float granite on water? We are about to decode the sophisticated engineering that turned impossible visions into stone reality. What does true ingenuity look like when stripped of all modern technology? Deep within the desert sands, the Great Pyramid stands as a testament to a forgotten science. Its construction was a symphony of coordinated effort, moving millions of limestone blocks into a structure aligned with celestial precision. This was not brute force, but the application of core engineering principles that transformed backbreaking labor into manageable tasks. The ancient masters understood leverage, using long wooden beams and stone fulcrums to lift weights that would otherwise be immovable. They employed the inclined plane, a simple ramp system that allowed workers to drag massive stones upwards, one gradual step at a time. These were the simple machines, the fundamental components of all complex engineering. According to expert Dr. Emily Carter, this was not guesswork. It was a profound, observational knowledge of physics and the properties of their materials. They knew how stone would fracture, how wood would bend, and how sand could both support and slide. This deep understanding became a living blueprint, passed not in written manuals, but through oral tradition and hands-on apprenticeship from one generation of builders to the next. A master stonemason would teach his apprentice not just how to cut a block, but why a specific angle would distribute weight more effectively. This accumulated wisdom, refined over centuries, laid the groundwork for every monumental structure that followed. It reveals a technological lineage, a chain of innovation stretching from the first lever to the soaring Gothic cathedrals of Europe. How did such detailed knowledge survive and spread across continents and millennia without a single universal language? The answer lies not in a library, but in the very stones themselves. That knowledge of leverage was a tangible force in the hands of ancient engineers. We see it in action with the first method, the brilliant application of leverage and counterweights. Think of a massive granite obelisk lying prone on the ground, its ultimate destination a vertical position pointing towards the gods. Using nothing but long wooden beams and carefully calculated stone counterweights, crews could initiate this incredible lift. They would slide levers under one end of the obelisk, using a stone block as a fulcrum, the pivot point that multiplies their force. With coordinated pushes, they would raise the stone just enough to pack support underneath. Then they would reset the levers, lift again, and pack more support, inching the colossal stone upwards in a series of controlled, manageable steps. This was not about raw strength, but about intelligent force multiplication. The Roman architect Vitruvius detailed these principles, explaining how a long enough lever could allow a single person to lift a weight that would otherwise require the effort of many. But leverage alone was not the entire story. The true genius emerged in the use of counterweights. Imagine a massive stone block suspended from a frame over the obelisk's base. As the obelisk was levered upwards, this counterweight would be gradually lowered, its immense mass providing a stable, balancing force that prevented the entire structure from tipping over uncontrollably. The successful erection of the Lateran obelisk in Rome stands as a monumental testament to this technique. How did these builders know where to place the fulcrum? How did they calculate the precise weight needed for the counterbalance? Their success reveals a deep, practical grasp of mathematics and physics. They understood the ratios of weight and distance, the principles of mechanical advantage that allowed them to achieve the impossible with simple, elegant tools. This was engineering stripped to its purest form, a dance of balance and force that turned stone and wood into the most powerful machines on Earth. The lever and counterweight solved the problem of lifting, but a greater challenge remained. How do you move a stone the weight of a small elephant hundreds of feet into the air? The answer was to cheat gravity, not by fighting it directly, but by outsmarting it with a longer, gentler path. This was the power of the inclined plane. Picture the landscape around a rising pyramid, dominated by earthen ramps that snaked their way up its flanks like colossal roadways to the sky. Workers, harnessed together, would drag massive stone blocks on wooden sleds along these gradual slopes. The ramp did not make the stone lighter, but it dramatically reduced the force needed to move it upwards by spreading the exhausting work over a much longer distance. Pulling a 1-ton block straight up a vertical face requires immense, instantaneous force. Pulling that same block up a long, gentle ramp requires a much smaller, sustainable force applied over a longer time. It was a trade of distance for effort, a fundamental principle these engineers mastered completely. They were not just building ramps, they were designing them. In both Mesopotamia and Egypt, the angle of the slope was a critical calculation. A ramp that was too steep would be impossible to climb with a heavy load. A ramp that was too shallow would require an immense, wasteful amount of material and length. They found the perfect balance, an angle that optimized both human effort and structural stability. Analysis of ancient construction sites reveals even more clever adaptations. To overcome the immense friction between the sled and the ramp surface, workers would often pour water onto the path ahead. This layer of mud acted as a powerful lubricant, turning a grueling, sticky drag into a surprisingly smooth slide. The bent pyramid in Egypt stands as a perfect case study in this evolving science. Its lower section has a much steeper angle than its upper section, and archaeologists believe this shift was accompanied by changes in ramp design. A different slope required a different ramp system, a different calculation of force and stability. This was not a one-size-fits-all operation, it was dynamic engineering. But what were these ramps actually made of? They were temporary giants constructed from the most available materials: mud brick, rubble, and desert clay, all packed and reinforced with wooden beams and matting. They were the ultimate disposable tools, built with immense effort only to be dismantled once the final capstone was set in place. This pragmatic approach to vertical transport reveals a mindset that saw no problem as insurmountable, only a path not yet built. While ramps conquered the vertical world, the vast horizontal distances presented their own monumental puzzle. Moving stones weighing hundreds of tons across miles of desert or river plain required a different kind of genius, one that turned the very ground into a fluid highway. This was the domain of rollers and sledges, a method of transportation so elegantly simple it remains profoundly effective. Teams of laborers would first construct a massive wooden sledge, a robust platform upon which the stone block would be securely lashed. The true magic, however, happened beneath it. They would place a series of sturdy logs acting as rollers directly in the sledge's path. As teams of workers or oxen pulled on great ropes, the sledge would glide forward over these rolling cylinders. The principle was a masterful reduction of friction. Instead of the sledge grinding relentlessly against the hard, uneven ground, it moved smoothly over the constantly rotating logs. Historical accounts from the Greek historian Herodotus vividly describe this very technique being used to transport the massive limestone blocks for the Great Pyramid. a logistical operation of staggering scale. The method was not without its own intricate challenges. It required a highly coordinated, rhythmic effort. As the sledge moved forward, rollers would emerge from the back. Workers had to quickly retrieve these freed logs and run them to the front, creating a continuous, rolling pathway that advanced with the load itself. It was like laying down a temporary, moving road made of wood. The transport of the famous Colossi of Memnon in Egypt stands as a silent testament to this system's power. These gigantic stone statues, each weighing over 700 tons, were moved hundreds of miles from their quarry to their final resting place. Using rollers, the engineers effectively turned an impossible drag into a manageable, albeit still Herculean, pull. The ground resistance was minimized, and the immense weight was distributed evenly across the surface of each log, preventing the colossal statue from sinking into the soft earth. This efficiency, however, came with a steep logistical price. How did ancient project managers secure a continuous supply of thousands of logs, especially in regions where large timber was scarce? The operation required not just strength, but sophisticated advance planning and a robust supply chain to source, transport, and constantly replace the wooden rollers on their long journeys. This was not mere brute force, it was a symphony of coordinated motion and resource management, all dedicated to making the earth itself roll away beneath the weight of stone giants. But even rollers and sledges had their limits when the destination was a high wall or a soaring arch. For the final, delicate act of placement, ancient engineers turned to a device that gave them both power and precision, the pulley. Imagine a single rope threaded through a grooved wooden wheel. By pulling down on one end of the rope, a worker could lift a heavy stone block attached to the other end. This simple redirection of force was a revolution. It meant that teams could stand on solid ground, using their full body weight to pull downwards, a far more stable and powerful position than trying to lift upwards. The real breakthrough, however, came with the compound pulley. This was a system of multiple wheels or sheaves arranged together. Each additional pulley in the system effectively divided the weight, meaning a small team could lift a load that would otherwise require the strength of dozens. A stone block weighing 1,000 pounds might feel like only 250 pounds to the workers pulling the ropes. This was not magic, it was pure mechanical advantage, a tangible reduction of effort through intelligent design. The Greeks and Romans perfected these systems, with texts from engineers like Hero of Alexandria detailing their intricate designs. These were not just theoretical concepts, they were the vital tools that built empires. The massive marble blocks of the Parthenon's entablature, the heavy stone lintels placed high above doorways, all were likely guided into their perfect positions by networks of ropes and pulleys. This precision was everything. A block lowered a fraction of an inch too far could shatter on the stone below, or worse, crush the workers beneath it. This leads to a crucial, often overlooked component of the entire operation, the rope itself. The entire system's safety and success depended on the strength of these fibrous cords. Ropes were engineered from materials like hemp, flax, and even papyrus, meticulously twisted and braided to create incredible tensile strength. The art of knot tying was equally vital. Specific, reliable knots that would not slip under immense strain were a form of life insurance on a construction site. A knot that came undone could mean the catastrophic release of a multi-ton weight. The evolution from a single pulley to a complex block and tackle system represents more than just a new tool. It signifies a fundamental shift in thinking. It was the move from moving mass to controlling it, from brute force to finesse. It allowed builders to place enormous stones with the careful deliberation of a jeweler setting a gem. How did these principles of controlled lifting eventually give rise to machines that could shape the stone itself? The final placement of a stone block relied on the precise control of pulleys, but the journey to that point demanded solutions for moving immense weights across vast landscapes. Water itself became one of their most powerful allies. In ancient quarries, engineers did not just cut stone, they designed entire hydraulic landscapes. They would dig channels right up to the quarry face, then use a simple, brilliant principle, buoyancy. A stone that was impossibly heavy on land became manageable, even buoyant, once it was floated on a barge. This was not about eliminating weight, but about letting water bear the load. The massive granite obelisks of Egypt, for instance, were often loaded onto specially built giant reed boats at the quarry. The channels would be intentionally flooded, the barge would rise with the water, and the stone was now afloat, ready for its journey. The true scale of this hydraulic engineering is staggering. To transport stones for great temples, engineers would sometimes divert entire rivers or carve out artificial canals that stretched for miles, creating liquid highways that led directly to the construction site. This was the ultimate labor-saving device. A few boatmen with poles could guide a barge carrying a 200-ton stone, a task that would have required thousands of laborers dragging it over land. The ancient Indus Valley civilization mastered this art, with their cities featuring sophisticated dockyards and canals that were clearly integral to their construction logistics. Even on remote Easter Island, while the iconic Moai statues were likely moved upright in a rocking motion, the smaller red stone topknots that crowned them were almost certainly rolled on logs or possibly floated on rafts across short stretches of water. This reliance on water raises a critical question of ancient science. How did they perform the necessary calculations? They had to understand displacement, the fact that a floating object pushes aside a volume of water equal to its own weight. They learned through observation exactly how deep a barge would sink when loaded, ensuring it had enough freeboard to handle waves without sinking. Managing water levels was a constant, delicate operation. Canals required sluice gates and dams to maintain a consistent, navigable depth. A sudden drop in water level could ground a barge and its priceless cargo, potentially cracking the stone or requiring a monumental effort to refloat it. This innovative use of a natural force reveals a mindset that saw the environment not as an obstacle but as a toolkit. They looked at a river and saw a pulling force. They looked at a floodplain and saw a potential canal. By harnessing the inherent power of water, these engineers transformed back-breaking transport into a fluid, almost graceful operation. The stones of Stonehenge rise from the English plain with a purpose that goes far beyond mere monument. Their alignment with the solstice sun is not a happy accident, but the result of deliberate, sophisticated geometric planning. To achieve this celestial accuracy, ancient engineers relied on a suite of precise tools and a deep understanding of shape and space. The groma, a simple yet brilliant Roman surveying instrument, allowed them to establish perfect right angles over long distances. It consisted of a cross-shaped frame suspended from a pole with a plumb bob hanging from the end of each arm. By sighting along the aligned bobs, a surveyor could mark out straight lines and 90-degree corners across an entire landscape. For measuring vertical angles and tracking celestial bodies, they used early versions of the astrolabe. These devices transformed the sky into a measurable grid, enabling builders to orient their structures with the cosmos. This knowledge was not just theoretical, it was intensely practical. As archaeologist John Romer points out, geometric principles like the Pythagorean theorem, the relationship between the sides of a right triangle, were being applied on construction sites for centuries before Greek philosophers ever formalized them in text. A builder might not have known the equation, but he knew that a triangle with sides measuring 3, 4, and 5 units would always create a perfect right angle. This empirical, hands-on geometry was the invisible framework upon which every stone was set. These precise measurements directly informed the design of the very machines that moved the stones. The angle of a crane's boom, for instance, was not arbitrary. It was a calculated decision, a geometric solution to the problem of how to lift a heavy load and swing it into a specific, predetermined position. The crane had to be more than just strong, it had to be accurate. This same geometric mastery is visible in the breathtaking sweep of Roman aqueducts. These structures march across valleys and hills for miles, maintaining a consistent, gentle gradient that kept water flowing steadily. Surveyors used tools like the Counterweights, a long, water-leveled table, to ensure this precise slope over vast, uneven terrain. A miscalculation of a single degree over 10 miles would have sent the water rushing backwards or left it stagnant. How did they maintain such unwavering precision from one end of a project to the other? They used a system of sighting poles and levels, creating a continuous chain of measurement that turned ambitious blueprints into stone and water reality. This was the ultimate fusion of knowledge and application, where abstract lines and angles became the bones of an empire. The invisible framework of geometry and precise measurement was only as strong as the materials it was built upon. Ancient engineers possessed an intimate, almost instinctual knowledge of stone itself. They were not just builders, they were master material scientists, selecting specific rock types for their unique properties with a strategic eye. An Egyptian obelisk demanded granite, a stone of immense compressive strength, capable of resisting fracture as it soared towards the sky. The Great Pyramids, however, reveal a more nuanced strategy. Their inner cores were built from softer, more abundant local limestone, while the outer casing and critical structural elements like the burial chamber were reserved for the far more durable granite and fine white limestone. This was not random selection, it was a brilliant allocation of resources based on a deep understanding of material performance. They knew that granite could withstand immense weight and weathering, while the softer core stone was perfectly adequate for the bulk of the structure, especially when it would be hidden and protected by a hard outer shell. Historical sources like Pliny the naturalist describe how Roman builders would actively test different types of stone, striking them with hammers to listen to the ring, a clear, sharp sound indicating a dense, strong material, while a dull thud might reveal hidden flaws or a softer composition. They studied how different stones fractured under stress, learning to read the natural grain and bedding planes to predict where a block would split most cleanly. This empirical testing was their laboratory. A stonemason would learn through a lifetime of hands-on work that sandstone was easier to carve but weathered more quickly, while basalt was brutally hard to shape but would last for millennia. How did they refine this knowledge without modern instruments? They observed. They watched how a specific type of limestone held up in a desert sandstorm over 50 years. They saw how a granite column settled under a century of weight. This accumulated generational observation became a living database of material properties. They learned that a stone's compressive strength, its ability to bear weight without crushing, was paramount for a supporting column. They understood that a stone's tensile strength, its resistance to being pulled apart, was critical for a lintel spanning a doorway. This profound, practical wisdom allowed them to match the right stone to the right task, ensuring that their monumental machines of stone would not just be built, but would endure. The stone itself was never just a building block, it was a vessel for belief. Ancient blueprints were layered with meaning, where every calculated angle and chosen material held a spiritual dimension. Engineering served a dual master, the need for structural integrity and the demand for ceremonial perfection. A temple was not merely a shelter, it was a physical conduit to the divine, and the machines that built it became sacred instruments in that ritual. The very act of construction was a form of worship, a repeated ceremony that connected the human world with the cosmos through architectural form. Scholars like Mircea Eliade observed that for ancient cultures, raising a monument was a profound reenactment of the creation of the world itself. The machines were extensions of this worldview, their levers and ramps infused with a purpose that went far beyond the physical. This cultural dimension directly shaped technical choices. The placement of a massive stone lintel over a temple doorway was not just a feat of strength, it was a symbolic act of bridging the earthly and the heavenly. The precision required to align a pyramid's passageway with a specific star was driven by a celestial imperative, a need to anchor the pharaoh's soul to the eternal cycles of the night sky. This intricate interplay between belief and engineering is visible in the Nazca lines of Peru. While not machines themselves, these vast geoglyphs etched into the desert floor demonstrate how immense, precise physical labor was directed by profound symbolic intentions. The creation of these lines required systematic planning, measurement, and execution on a grand scale, all to produce designs that could only be fully appreciated from a perspective beyond the human, from the realm of the gods. The techniques used to clear the dark surface stones and reveal the lighter earth beneath were a form of landscape engineering in service of a spiritual vision. The same mindset that guided the creation of the Nazca lines influenced the builders of Stonehenge and the Great Pyramids, where the machine's function was inseparable from its symbolic role. The choice of a specific quarry for its stone might be based on the rock's color, associated with a particular deity, not just its compressive strength. The rhythmic, coordinated pulling of ropes to move a statue might be accompanied by chants and prayers, turning a laborious task into a sacred procession. How did the need for perfect celestial alignment influence the design of their surveying tools? The answer lies in seeing these ancient engineers not merely as technicians, but as architects of both stone and spirit, whose greatest machine was a culture unified in its pursuit of the divine. The raising of an obelisk was a final, breathtaking act of orchestrated power. At the quarries of Aswan, workers first freed the single piece of granite from the bedrock. They did not use saws, but a more patient method. Teams would hammer wooden wedges into a line of holes drilled along the desired fracture line. Then they poured water over the wedges. The wood would swell with tremendous gradual force, cleanly splitting the stone from the earth. The rough obelisk was then loaded onto a massive sledge for its long journey north, a trip that could take months, floating on a specially built barge down the Nile. Upon arrival at the temple site in Thebes, the true engineering challenge began. The monolith, lying prone on its side, had to be raised to a vertical position without a single crack. The engineers prepared a deep foundation pit, its base a socket designed to receive the obelisk's point. They then built a gigantic, temporary mound of earth and rubble against this pit, its slope carefully calculated. The sledge bearing the obelisk was dragged up this earthen ramp until the stone's base hung directly over the foundation socket. Now came the moment of truth. Using a complex system of levers and ropes, crews began to tilt the obelisk downwards. Its base would descend into the socket, guided by the earthen walls of the mound that cradled it, preventing a disastrous, uncontrolled fall. As the stone pivoted, the mound itself was crucial. It supported the immense weight during the delicate pivot and was gradually excavated from the front as the obelisk approached vertical, allowing it to settle perfectly into place. The entire process was a symphony of counterbalancing forces. Reliefs and inscriptions suggest the use of massive counterweights on the high end of the obelisk to assist the controlled descent, a system requiring precise calculation of mass and angle. A single miscalculation in the weight of the counterbalance or the stability of the earthen guide could have sent hundreds of tons of stone crashing down, destroying years of work and shattering the divine symbol. The successful erection of an obelisk like Cleopatra's Needle was therefore more than a construction project. It was a very public demonstration of the pharaoh's ability to command both nature and men, a direct statement of power blessed by the gods. The incredible stability and longevity of these stones, standing for millennia, offer a powerful lesson for modern engineers. They teach the profound value of understanding material limits, the elegance of using gravity and counterbalance, and the unmatched durability that comes from a perfect marriage of purpose, material, and method. What other forgotten principles of permanence are encoded in these silent stone giants? Roman cranes transformed construction sites into theaters of coordinated human power. The most iconic of these machines was the treadmill crane, a wooden giant where men walked endlessly inside a large, spoked wheel. Their collective stepping motion turned the wheel's axle, which was wound with a heavy rope connected to a complex system of pulleys high above. This was the polyspatos, a compound pulley system that multiplied the force of those walking men into enough lifting power to hoist multi-ton stone blocks. The Roman architect Vitruvius detailed how this mechanical advantage worked, explaining that with multiple sheaves in the pulley block, the load felt dramatically lighter to the workers inside the wheel. A stone weighing thousands of pounds could be lifted by a team whose individual effort felt like lifting only a few hundred. This was not about working harder, but about working smarter through brilliant machine design. Archaeological evidence, like stone reliefs from tombs in ancient Rome, clearly depicts these cranes in action, their wooden frames and dangling ropes permanently carved into history. They were not rare experiments, but standard equipment on the grand imperial projects that defined an era. The immense stone arches of the Colosseum, the perfectly set voussoirs that formed its soaring vaults, all depended on the precise placement these cranes provided. The famous Roman concrete, poured into wooden forms, often required massive formwork and reinforcement that only such a crane could lift and hold in place until the material set. The operation of these machines demanded rigorous safety protocols and flawless coordination. A single misstep inside the treadwheel could cause a sudden, catastrophic release of tension, sending a stone block plunging to the ground. Communication was managed through a system of shouts and signals from a foreman, ensuring the walkers moved in perfect unison and the load was raised, swung, and lowered with exacting control. The men inside the wheel had to match each other's pace perfectly, their synchronized steps a matter of life and death for everyone on the site below. This intricate dance of human movement and mechanical power enabled the Romans to build with a speed and scale that would dominate the landscape for centuries. How did these principles of organized labor and machine design echo through later ages to build the cathedrals of the medieval world? The heavens were not just a spectacle for ancient engineers, they were a master blueprint. At places like Chanquillo in Peru, 13 stone towers march along a desert ridge, functioning as a sophisticated solar calendar. The precise positioning of each tower required more than just ritual observance. It demanded exacting engineering to ensure the sunrise and sunset would align with specific gaps at the solstices and equinoxes. This celestial choreography was embedded into the very bones of their structures. Mayan pyramids like El Castillo at Chichen Itza are famous for the serpent of shadow that slithers down their steps during the equinoxes. This was not an accidental byproduct, but a calculated effect achieved through meticulous architectural alignment. The pyramid's design served a dual purpose. It was a monumental temple and a giant stone timekeeping device. This deep integration of astronomy and engineering meant that the machines used to build these structures had to be just as precise. A crane lifting a lintel stone for a temple doorway was not merely placing a rock, it was positioning a component in a vast astronomical instrument. The calibration of these devices was critical. A ramp used to drag stones for a solstice-aligned wall had to account for the sun's changing position throughout the year, ensuring construction could proceed without casting critical surveying lines into shadow. The Greek astronomer Ptolemy wrote extensively on the mechanics of the cosmos, and his work implicitly connected the movement of celestial spheres to the principles of leverage and force on Earth. For these builders, engineering and cosmology were two sides of the same coin. This celestial framework even dictated construction timelines. The transport of the bluestones to Stonehenge, for instance, was a monumental journey. But their final placement was guided by astronomical markers. The great axis of the monument points to the summer solstice sunrise, meaning the entire layout, and thus the machinery used to erect the stones had to be oriented to this cosmic north. The levers, ropes, and ramps were all employed not just to lift but to align. How did they translate the arc of a star into a foundation trench? They used simple, powerful tools like gnomons, shadow-casting poles, to track the sun's path across the seasons, translating celestial motion into terrestrial measurements. This ensured that when the final stone was set, the entire structure would breathe in time with the universe, a machine of stone built to track the eternal dance of the heavens. The theoretical foundations for these stone-moving machines were meticulously recorded by Greek thinkers who saw the universe as a system of mechanical principles. Archimedes, perhaps the most brilliant of these minds, did not just invent, he formalized the underlying laws of leverage and buoyancy. His famous declaration about moving the world with a lever long enough was not mere boastfulness. It was a profound statement of belief in the power of mechanical advantage. His writings provided the mathematical proofs for why a lever works, transforming a practical tool into a predictable, scalable technology. This shift from empirical knowledge to codified theory was a revolution. It meant that an engineer did not have to rely solely on handed-down tradition. He could study the principles and design new machines based on established laws. The survival of Archimedes' work, along with the prolific texts of Hero of Alexandria, became a critical bridge between ancient empires. Hero's pneumatica and mechanics described a wondrous array of devices, from the simple windlass, a rope winch used to lift heavy loads with a crank, to the sophisticated Archimedes screw, a helical pump that could move water uphill. These were not just curiosities, they were potential construction tools. A windlass could be adapted to provide the controlled pulling power for a crane's rope, while the principles of the screw could inspire methods for moving earth or even adjusting the position of heavy stones with fine precision. The dissemination of this knowledge was a fragile, human-powered process. Scribes in Alexandria and later in Byzantine and Arab centers meticulously copied these precious manuscripts onto parchment and papyrus, word for word and diagram for diagram. Each copy was a lifeline, preserving the blueprints of ingenuity across wars, fires, and the slow decay of time. How did a text from Syracuse find its way to a medieval monastery? It traveled along trade routes, was carried by scholars, and was translated across languages, from Greek to Arabic and eventually to Latin, ensuring that the mechanical legacy of Greece would eventually fuel the building boom of the Romanesque and Gothic eras. This fusion of Greek theory with Roman and medieval practicality created an unbroken chain of innovation, where the written word empowered generations of builders to reach for the sky. Deep within the quarries, the stone itself had to be mastered before it could ever become part of a machine. Workers faced immense granite cliffs, knowing they needed to extract colossal blocks with near-perfect precision, avoiding the hidden faults that could shatter a year's work in an instant. Their primary tools were surprisingly simple, yet devastatingly effective. They used dolerite hammers, hard stone balls attached to wooden handles, to pound away at the bedrock. By repeatedly striking along a straight line, they would create a deep groove or channel, but the true genius lay in what came next. Into these channels, they would drive dry wooden wedges. Then they poured water over them. The wood would swell with a slow, immense, and irresistible force, a power that patiently and cleanly split the granite along its natural grain. This method harnessed nature's own physics to do the hardest work, transforming a solid mountain into manageable, movable pieces. For finer shaping, they employed copper saws. These were not like modern serrated blades, but long, flat strips of copper that were pulled back and forth. The cutting power did not come from the soft metal itself, but from an abrasive slurry of sand and water that was fed into the cut. The hard quartz particles in the sand did the actual grinding, while the copper saw simply served as a carrier, steadily wearing a precise line through the toughest stone. The choice of quarry site was a strategic decision of the highest order. Engineers sought out locations with the highest quality stone, free of cracks or weaknesses, but they also had to consider the logistics of moving multi-ton blocks. Proximity to a river or the sea was often a deciding factor, as it promised a ready-made water highway for transport. The quarry at Baalbek in Lebanon offers a staggering testament to this organized ambition. There, the so-called stone of the pregnant woman lies in its quarry, a single block estimated to weigh over 1,000 tons. The mere act of extracting such a monolith speaks to a breathtaking level of planning, labor coordination, and tool technology. How did they isolate a block of that size from the living rock without generating catastrophic internal stresses? The answer lies in the meticulous process. They would undercut the block, carving out tunnels beneath it and leaving only supporting pillars of stone. Then, using their wedges, they would carefully sever these final connections, allowing the block to settle evenly onto a prepared bed of sand or rubble, a controlled descent that prevented a damaging shock. This quarrying phase was the critical first link in the chain. A flaw introduced here would doom the entire project, no matter how brilliant the ramps or cranes that followed. The quarries were the birthplaces of the stone machines, where raw material was transformed with foresight and skill into the components of immortality. The immense power of an ox team was a force of nature harnessed by ancient engineers. Tomb paintings from Egypt show long lines of these powerful animals, their shoulders straining against heavy ropes as they drag colossal stone blocks on wooden sledges. This was not a simple substitution of animal for man. It was the creation of a hybrid machine, a living engine integrated into a larger mechanical system. These animals provided a consistent, powerful pulling force that human teams simply could not match, enabling projects of a scale previously unimaginable. Historical accounts describe how elephants, with their immense strength and intelligence, were employed in India and the Near East for tasks that demanded both power and precision. They could be trained to push heavy logs into position or to walk in circles, turning a massive capstan, a rotating winch that wound up a heavy lifting rope. Horses and donkeys, prized for their speed and endurance, were the backbone of logistics, transporting materials across long distances to the construction site. This strategic use of animal power fundamentally changed the economics of building. A single team of oxen could replace dozens of laborers, freeing up human workers for more skilled tasks like stone dressing or precise placement. The construction of the great Mesopotamian ziggurats, towering stepped pyramids of mud brick, would have relied heavily on these animal trains to bring millions of bricks from distant brickyards. But how did they ensure these living machines were both reliable and efficient? The breeding and training of these animals was a science in itself. Oxen were selected for their docile temperament and sheer physical power, then painstakingly trained to respond to vocal commands and to pull in perfect unison. A disobedient or panicked animal in the middle of a pull could break the rhythm, snap vital ropes, or cause a disastrous runaway load. Specialized harnesses were developed to distribute the pulling force across the animal's body effectively, preventing injury and maximizing the transfer of power. The integration of animal energy was a masterstroke of ancient logistics, a key adaptation that turned ambitious architectural dreams into tangible stone reality. This living component completed the machine, merging the strength of the beast with the intelligence of the engineer to move mountains, one steady pull at a time. The journey of Stonehenge's bluestones stands as one of history's great logistical puzzles. Each of these massive stones traveled over 150 miles from the Preseli Hills in Wales to the Salisbury Plain in England. How did ancient engineers move these multi-ton megaliths across such a vast and varied landscape without the wheel or domesticated animals? One compelling theory involves a system of wooden rollers. Teams would have laid down a path of logs, dragging the stone-laden sledge forward, then constantly recycling the freed rollers from the back to the front. This created a moving road of wood, a method effective on flat ground but immensely challenging over hills and through bogs. Another hypothesis suggests the use of sledges on specially constructed timber rails, greased with animal fat to reduce friction. This rail system would have provided a more stable and guided track, potentially making the haul more efficient over long distances. Some researchers have even proposed the use of ice tracks during winter months, where the stone could be slid over frozen pathways, though this theory is highly dependent on specific climatic conditions. Recent experiments by teams from University College London have put these ideas to the test. They constructed a replica sledge and track, discovering that a team of around 20 people could move a 1-ton stone at a steady pace. Scaling this up for the larger bluestones, however, would have required a coordinated effort of hundreds, rotating in shifts, and a sophisticated supply chain to provide food, water, and replacement timber. This was not a haphazard effort but a meticulously planned operation. The sheer difficulty of the journey forces a deeper question: why go to such extraordinary lengths? The answer likely lies in the cultural and spiritual significance of the stone itself. The bluestones were not just building material, they were considered sacred, imbued with power believed to be connected to their place of origin. This profound motivation transformed an engineering challenge into a pilgrimage, a ceremonial act that justified the immense investment of labor and time. How did they navigate the formidable obstacle of a river crossing? They may have used the buoyancy of log rafts, floating the stones on waterways for parts of the journey, then returning to the grueling land-based haul. Each theory offers a glimpse into the ingenuity of these prehistoric engineers, yet the complete picture remains an enduring enigma, a silent testament to a capability we are still striving to fully comprehend. Mathematical precision was the silent partner in every engineering triumph. The Great Pyramid of Giza encodes the constant pi in the ratio of its perimeter to its height, a relationship that reveals a deep, if intuitive, grasp of geometric principles. This was not a coincidence. It was the result of a rigorous mathematical framework that informed every blueprint, from the length of a lever to the gentle slope of a ramp. Ancient engineers used arithmetic and geometry as practical tools to solve tangible problems of force and mass. The Rhind mathematical papyrus from Egypt reads like an engineer's manual, filled with problems on calculating the slope of a pyramid, the volume of a cylindrical granary, or the amount of stone needed for a specific structure. These were not abstract academic exercises. They were the essential calculations that determined a project's feasibility and safety. To design a lever capable of prying up a 100-ton obelisk, a master builder needed to know exactly where to place the stone fulcrum. The ratio of the lever arm on either side of that pivot point directly determined the mechanical advantage, the factor by which their effort was multiplied. A miscalculation here meant the lever would not budge, or worse, would snap under the strain. They used proportional reasoning for this, a form of mathematics that deals with ratios and relationships. If a 1-cubit-long lever could lift a 100-pound weight, then a lever 10 cubits long could, with the fulcrum correctly placed, lift a weight 1,000 times heavier. This same logic applied to the design of ramps. The incline was a critical calculation. A ramp's steepness directly correlated to the force required to drag a sledge upwards. Builders needed the gentlest possible slope to minimize effort, but a slope that was too shallow would require an impossibly long and materially wasteful structure. They solved for the optimal angle, a perfect balance point between human endurance and logistical reality. This required a standardized system of measurement. How could a team in Aswan communicate a ramp design to a team in Memphis without a shared unit of length? The cubit, the length from a man's elbow to the tip of his middle finger, became that standard. Royal cubit rods made of stone or precious wood were the master copies against which all other measuring sticks were calibrated. This ensured that a blueprint for a machine, whether a lever or a crane, was reproducible and scalable from one project to the next, from one generation to the next. The mathematics behind the machine was what turned a singular act of genius into a repeatable, reliable technology that could shape the world. True engineering genius often lies in adaptation rather than invention. High in the Andes Mountains, Inca builders faced a landscape of impossible slopes and shifting soils, yet they constructed Machu Picchu and a vast network of roads without the wheel or iron tools. Their greatest machine was the mountain itself. Instead of fighting the terrain, they integrated with it, cutting stones to fit the irregular contours of the living bedrock. This meticulous fitting acted as a permanent, natural formwork, locking the structure into place and dramatically reducing the need to move massive blocks over long distances. The stones were not merely placed upon the mountain, they became part of it, a symbiotic relationship between human design and geological reality. This approach required a deep, intimate knowledge of local materials. They understood which quarries provided the most stable granite, how to split it along its natural fault lines, and how to shape it with simple stone hammers until it clicked perfectly into its neighbor. But how did they move the stones they did need to transport across such treacherous ground? The answer was in their customized sledges and roads. They built extensive staircases and causeways, often paving them with fitted stones to create a smooth, stable surface for dragging heavy loads. In snowy regions, they might have used sleds designed to glide over compacted ice, while in other areas they leveraged gravity itself, carefully lowering stones down steep inclines using ropes anchored to rock protrusions. The famous Inca rope bridges woven from local grasses were not just for people, they were testaments to a material science that used flexible, renewable resources to solve immense logistical challenges. Every project was a conversation with the environment. An engineer would assess the soil stability before building a ramp, knowing that soft ground required a wider base to distribute the weight. They learned seasonal weather patterns, planning transport for the dry season to avoid muddy, impassable tracks. This was an iterative process of observation and refinement. If a retaining wall showed signs of stress after a heavy rain, the next wall would be built with a different angle or a stronger foundation. They learned from failure and success, codifying this environmental wisdom into a living tradition that ensured their structures were not only monumental but also resilient, built to endure the tremors and torrents of their world. This profound adaptability, this ability to listen to the land and design in harmony with it, may be the most powerful blueprint they left behind. Behind every stone machine stood a human machine of breathtaking complexity. The construction of a pyramid was not just an engineering project, it was a feat of social organization on an epic scale. A rigid hierarchy kept the entire operation running, with a chief overseer at the apex, a master of works who understood the grand blueprint. Beneath him were layers of scribes recording supplies and progress, and specialized foremen who each managed a specific crew. These crews were the heart of the operation, divided into artisans, the skilled stonemasons and carpenters, and the vast labor force that provided the raw muscle. This division of labor was not arbitrary. It was a sophisticated system designed to maximize efficiency. An artisan did not waste his expertise hauling rubble, and a laborer was not asked to perform a delicate cutting task for which he was untrained. Each person had a specific, repeatable role, turning chaos into a coordinated symphony of effort. This social machinery was so advanced that workers lived in dedicated settlements right next to the construction site. At Giza, the workmen's village was a planned community with bakeries, breweries, infirmaries, and even houses for the skilled workers and their families. Inscriptions found there list the names of crews with proud, competitive titles like the Friends of Khufu or the Drunkards of Menkora. These were not anonymous slaves but organized, valued teams. This highly structured society was the operating system for the physical machines. The synchronized pull of 100 men on a rope, the rhythmic stepping inside a giant treadmill crane, the coordinated levering of an obelisk, all of it required flawless communication. How did a foreman direct a team he could not even shout over? They likely used a system of signal drums, horns, or colored flags to relay commands across the vast, noisy site. A specific beat on a drum might mean pull, while another meant hold, ensuring that every ounce of force was applied in perfect unison. This level of coordination transformed a scattered crowd into a single, powerful engine. But how did they motivate and sustain this workforce, especially when much of the labor was a form of corvée duty, a tax paid in work rather than goods? The evidence suggests a system of incentives. Workers were paid in bread, beer, fish, and other rations, with higher skilled artisans receiving larger and better quality portions. There was also a powerful cultural and religious motivation. Participating in the pharaoh's eternal project was a sacred duty, a guaranteed path to honor in the afterlife. This combination of material reward and spiritual purpose created a powerful, sustainable drive. The true blueprint for these stone machines was not just carved in papyrus, it was written into the very social fabric, a testament to the fact that the most complex machine of all is a society united in a single, monumental goal. That sophisticated social machinery could never have functioned without an equally advanced toolkit in its hands. The steady percussion of stone hammers gradually gave way to the sharp ring of metal, a transition that fundamentally altered the relationship between the builder and the stone. With the advent of bronze chisels and later iron saws, engineers moved from merely fracturing rock to shaping it with newfound precision. This was a shift from brute force to controlled incision, allowing for intricate joinery and smoother surfaces that made every subsequent step more efficient. A block shaped with a metal tool fit more perfectly with its neighbor, reducing the need for shims and adjustments during placement, which in turn made the levers, ramps, and cranes far more effective. The evolution of these handheld tools was the critical link that transformed a grand blueprint into a tangible, polished reality. The true breakthrough came with advances in metallurgy. Early copper tools were too soft to work hard stones like granite for long, but by alloying copper with tin to create bronze, and through sophisticated work hardening techniques where the metal was repeatedly hammered and heated, smiths produced chisels and saws that could hold a sharp edge. This durability was a force multiplier. A single, well-made bronze chisel could dress many stones before needing repair, while a soft copper one would deform after minimal use. This reliability allowed for more ambitious designs. In Egypt, the development of the tubular drill was a direct result of this improved metallurgy. This ingenious tool was a hollow tube of copper, likely used with a bow to spin it back and forth. Workers would feed an abrasive slurry of sand and water into the contact point. The hard quartz particles in the sand did the actual cutting, grinding a circular groove into the stone. As the tube drilled deeper, it would leave a solid core of stone in the middle that could be broken free. This method enabled the creation of precise holes for everything from locking joints to the attachment points for lifting ropes, seamlessly integrating the tool's function with the machine's operation. This synergy between tool and machine accelerated architectural possibilities across the ancient world. A stone perfectly squared with a metal chisel would slide more predictably on a sledge. A block with drilled lifting points could be safely and securely hoisted by a crane. The efficiency gained in the quarry and the dressing yard compounded at the construction site, saving immense amounts of time and labor. This tool-making revolution was not confined to cutting edges. The development of precise measuring instruments like metal-scribed cubit rods and bronze calipers ensured that every component, from the smallest tool part to the largest stone block, adhered to a universal standard. How did this tool innovation influence machine design? It allowed for greater complexity. The intricate gears and pivots of later Roman cranes relied on metalworking skills that first honed simple chisels. The confidence to attempt a perfectly smooth granite sarcophagus arose from the proven ability of abrasives and drills to finish the job. This was a virtuous cycle of innovation, where better tools enabled more refined machines, which in turn inspired the need for even better tools. The entire technological landscape of the ancient world was being quietly reshaped, one sharpened metal edge at a time, paving the way for structures of breathtaking sophistication. The chisel and the crane worked in perfect harmony, where artistic vision directly shaped the machines that built our world. In the temples of ancient India, we see this relationship carved into stone itself. Towering gateways or gopurams are covered in thousands of intricate figures of gods and goddesses, each one requiring the stone to be undercut and pierced with breathtaking delicacy. This was not decoration added after the fact, it was integral to the structure's purpose. To achieve this, engineers had to design lifting devices and support systems that could position these sculptural masterpieces without a single crack or chip. The aesthetic goal drove the engineering innovation. A block destined to become a dancing Shiva with its fine, extended limbs could not be manhandled like a plain foundation stone. It needed a custom cradle, a carefully calibrated system of ropes and pulleys that would lower it into place with the gentle precision of a jeweler setting a precious gem. This collaboration between artist and engineer was a dialogue of constraints and creativity. The artist dreamed of impossibly thin stone screens, like the jolly lattices found in Islamic architecture, which filter sunlight into geometric patterns. The engineer had to determine the absolute limits of the material, calculating the minimum thickness a sandstone panel could have while still supporting its own weight and resisting the wind. They learned to read the stone's natural grain, orienting the carving to work with the material's strength, not against it. Medieval European stonemasons left behind records that speak to this deep respect. A master carver would note that trying to force a delicate curl of stone against its natural bedding plane was an invitation for it to snap. The solution was often a new tool or a new machine, a special clamp to hold the fragile piece during lifting, or a finer-toothed saw that allowed for more detailed work. How did they translate a spiritual concept into a physical form without compromising either the vision or the structure? They understood that the two were inseparable. The soaring height of a Gothic cathedral spire was an expression of divine aspiration, but it was also a brilliant engineering solution for distributing weight. The exquisite carvings around a portal were not merely ornamental. They often served as keystones, locking the arch's complex forces into a state of perfect balance. This fusion of disciplines created spaces that do more than simply stand. They inspire, proving that the ultimate purpose of their stone machines was to elevate the human spirit. Those intricate stone lattices and soaring arches were not born in isolation. Across the vast networks of the Silk Road, ideas traveled as swiftly as spices and silks. Blueprints for sophisticated pulley systems perfected in the workshops of China gradually made their way westward, transforming construction sites in the Mediterranean. These trade routes were not just for goods, they were the information superhighways of the ancient world, carrying the most valuable cargo of all, engineering knowledge. A caravan master might not only deliver a load of rare incense, but also a scroll detailing a new method for counterbalancing heavy loads, or a verbal account of a revolutionary crane design seen in a distant kingdom. This constant flow of information enriched local building traditions, creating a fertile ground for innovation. The most profound example of this exchange is the architectural arch. While the basic concept was known in Mesopotamia for centuries, it was the Romans who encountered it, studied its principles, and then transformed it into the cornerstone of their empire. They did not merely copy the idea, they engineered it to a new scale and purpose, combining it with their own material science like concrete, to create the vast aqueducts and colossal amphitheaters that define their legacy. This was not theft, it was adaptation, a process of cross-cultural pollination that yielded something entirely new and more powerful. Maritime trade expanded this exchange across oceans. Roman forums gleamed with marbles imported from Greece, Egypt, and Anatolia, their transport requiring shared knowledge of shipbuilding, buoyancy, and harbor logistics between different cultures. Stonemasons and engineers themselves sometimes traveled with these precious stone cargoes, their expertise a tradable skill that introduced foreign techniques directly onto local soil. How did these interactions lead to hybrid machines? A Persian water-lifting device, the Noria, might inspire the gear system for a Roman crane, a design for a more efficient sledge, developed for moving stones across the Egyptian desert, could be adapted with local materials by Anatolian builders for their own temple complexes. This knowledge exchange was the ultimate catalyst, proving that the greatest structures ever built were not the product of a single brilliant mind, but the accumulated genius of countless cultures, all connected by the restless movement of trade. Beyond the levers and ramps lies a more mysterious realm of ancient engineering. Legends whisper of devices capable of softening stone with sound or levitating blocks with harmonic vibrations. These are the stories of lost technologies, hypothetical machines that challenge our entire understanding of the past. Consider the Baghdad battery, a simple clay jar containing a copper cylinder and an iron rod. When filled with an acidic liquid like vinegar, it produces a small electrical charge. While its true purpose remains debated, its existence opens a tantalizing question. Could ancient engineers have harnessed electroplating to gild sacred objects, applying a thin layer of gold onto statues with a primitive form of electricity? Across the Mediterranean, the writings of Hero of Alexandria describe an eolipile, a spinning sphere powered by steam. It was treated as a philosophical toy, but the underlying principle was a working steam engine. The potential was there, waiting to be scaled and applied. What if these ideas were not isolated curiosities, but glimpses of a wider, forgotten technological landscape? Some researchers point to sites like Puma Punku in Bolivia as potential evidence. Its stone blocks are interlocked with such geometric precision, with cuts so sharp and surfaces so smooth, that they seem to defy the capabilities of simple copper tools. This has led to speculative theories about advanced diamond-tipped saws or even the use of resonant sound waves to make granite temporarily malleable, allowing it to be molded like clay. The mainstream archaeological view, however, remains cautious. It emphasizes that the proven methods of rollers, ramps, and immense human effort are sufficient to explain these wonders. Anomalies like Puma Punku's precision could be the result of techniques we have simply underestimated, of skills and abrasives lost to time rather than a grand, high-tech collapse. The challenge for any historian is navigating the thin line between myth and plausible lost science. How do we distinguish a folk memory of a real technology from pure fantasy in the absence of physical evidence? We look for consistency, for multiple cultural references to similar devices, and for a logical path from known tools to the speculative ones. Exploring these possibilities is not about replacing proven facts with science fiction. It is an exercise in open-mindedness, a reminder that the full scope of ancient ingenuity may be far wider than our textbooks currently allow. The true lost technology might not be a specific machine, but the revolutionary mindset that first conceived it. That enduring legacy of ancient engineering offers a powerful lesson in sustainability, a design principle written not in blueprints but in the landscape itself. These stone-moving machines operated on a closed-loop system, leaving a remarkably light footprint on the earth. The ramps were built from local mud brick and desert rubble, materials that could be effortlessly returned to the environment once their job was done. The levers and sledges were crafted from renewable timber. The primary fuel source was a combination of human ingenuity and animal power, generating no carbon emissions beyond the breath of the workers and their oxen. Every component was either biodegradable, reusable, or sourced directly from the immediate vicinity. This stands in stark contrast to the immense energy demands of modern construction, with its global supply chains, fossil fuel-powered cranes, and concrete production that accounts for a significant portion of the world's carbon dioxide emissions. The ancient approach was inherently circular. A wooden roller worn down from moving a 100-ton block could be repurposed as a structural beam or simply left to decompose. The stone itself was quarried with a profound respect for the material, minimizing waste by using every possible fragment for rubble core or smaller structures. There were no sprawling landfills filled with construction debris, only the silent, enduring monument and a landscape allowed to heal. Today, a growing movement of green architects is looking back to these methods for inspiration. They are revisiting the use of locally sourced stone and timber, reducing the environmental cost of transportation. They are exploring passive solar design, a principle the ancients understood intuitively when they aligned their buildings with the sun's path. The modern concept of designing for deconstruction, where buildings can be easily taken apart and their materials reused, echoes the temporary, reusable nature of those ancient earthen ramps. The question for our time is profound. How can we merge our advanced technology with this timeless wisdom? We possess knowledge the ancients never did, but we have lost their innate sense of balance with the natural world. The lesson is not to abandon our cranes for levers, but to adopt their mindset of radical efficiency and local resourcefulness. It challenges us to see the environment not as an obstacle to be conquered with brute force, but as a partner in creation. Sustainable engineering, it turns out, is not a modern innovation, but the rediscovery of a very old and very wise way of building. The real test of these ancient blueprints comes not from texts, but from the strain of modern muscles and the groan of authentic timber. Across the globe, teams of archaeologists and engineers have embarked on an extraordinary mission to physically reconstruct the machines of the past using only the tools and materials available at the time. One of the most ambitious of these experiments was the Nova Pyramid Challenge, where researchers attempted to raise a 25-ton obelisk using a massive earthen ramp and a system of levers and counterweights. The theory seemed sound on paper, but the physical reality was a profound lesson in the hidden variables of ancient engineering. They discovered that the consistency of the ramp material was critical. A mix of mud and gravel that was too dry would crumble under the heavy sledge, while a mix that was too wet would turn into a slick, unworkable mire. The successful lift depended on a rhythm that could not be found in any manuscript, the precise timing of the teams operating the levers, and the careful, incremental lowering of the counterweight. A single misstep, a single rope pulled out of sequence, could have sent the entire stone crashing down. This hands-on testing transforms abstract theories into tangible, sweat-drenched reality. Similarly, the various attempts to move a Stonehenge bluestone replica have revealed the immense importance of team coordination and morale. Moving a 1-ton stone over level ground requires significant effort, but moving it across the varied terrain of the Welsh countryside demands something more, an almost intuitive communication between the pullers. The experiments showed that the pace had to be set by a leader's chant or drumbeat, creating a unified rhythm that turned individual effort into a single, powerful force. Minor adjustments, like regularly rotating the wooden rollers to prevent them from flattening under the immense pressure, proved to be absolutely vital, details that are rarely mentioned in historical accounts but are the difference between success and failure. These reconstructions do more than just prove a method was possible. They reveal the social and psychological dimensions of ancient labor. They show us that the true machine was not just the lever or the sledge, but the synchronized will of the people using them. How many other subtle, human-centered techniques have been lost to time? Techniques that turned a theoretical blueprint into a living, breathing achievement. The silent endurance of these stone giants is their final lesson to us. We have traced the path from the first lever prying a block from the earth to the celestial alignment of a finished temple, uncovering a world where engineering was a symphony of intellect, muscle, and spirit. These ancient blueprints reveal a profound truth, that true innovation is not about the complexity of your tools, but the depth of your understanding. They knew the physics of a lever, the strength of a granite vein, and the unbreakable power of a coordinated community. This was a sustainable, resilient form of creation, built on principles that harmonized with the world rather than conquering it. As we face our own challenges of construction and climate, their legacy offers a powerful compass. It points us toward designs that are efficient, durable, and deeply connected to their environment. Let the curiosity that moved these mountains of stone inspire your own pursuits. The greatest machine they built was not made of wood or rope, but of an unwavering human spirit determined to reach for the sky. Thank you for joining this exploration into our shared past. If these stories of ingenuity resonated with you, please share your thoughts below and support the channel by liking and subscribing for more journeys into the mysteries of history.